Hello, everyone, and welcome back to Historical Geology 1404. Today, we are doing our last review day. We are talking about sedimentary environments. So we reviewed sedimentary rocks and simple sedimentary structures in our last lecture. And now we're going to take all of that and tie it into a more holistic viewpoint, how we take things like this is this kind of sedimentary rock and it contains this sedimentary structure and interpret an environment out of that data. Okay, so yeah, today is a lot of review, but you're also going to be getting some new stuff. All right, specifically how kind of the second half, how to finish your thought, so to speak. Why do we care about the sedimentary rock? Why do we care about the structures? Because they look pretty? No, because we can get something out of it. What are we getting out of it? That's what we're talking about today. All right. A few housekeeping announcements. This is lecture 4. This is the last lecture of module 1. That means you get an exam on Thursday, 2 days from now, if you're watching this in the online class. Okay. Whatever the due date is on your Blackboard shell if you're watching this further in the future. Okay. So the next time we meet, it will be an exam review. Okay. And it will probably be short. I'm going to have to do the math because this semester started off on a weird day for us. It started on a Thursday for us, which is really weird. Okay. Because of that, I think that I have been robbed of a day with you. So I'm going to double check my math on that. And if that is true, then I may combine our review the next time we meet with the next lecture. I will still open the review on Thursday, or the exam on Thursday, but I may need to throw the next lecture in there to make sure that we end on time this semester. I'll let you know on Thursday if that's the case. But either way, we will have a review session, be that long or short. Please bring your notes. For my students that watch this online, send me emails with your questions. If you do not ask questions, I can't address your questions. For those of you that may not have been in my class for a while, my reviews are based entirely upon the questions that my students bring to the table. I do not have a review sheet. I do not have a review outline. I do not have anything like that. The best way for you to get what you need and for me to know how much you've been keeping up is for you to ask your questions and let that be the guide for our review. You cannot use anything except your notes on the exams, so please make sure that they are strong notes. What else? I can't think of any other business. Anyone have anything they want to share with the class or bring to the table before we begin? No? All right, well, let's jump right on in. What you're looking at here in these pictures are, first of all, I think they're beautiful, right? Layers of rock. It almost is like someone painted them, right? But the ways that they are layered on top of each other and the interactions you can see between them, the differences between them, do in fact paint a picture of sorts. No one took a brush to it. But the picture that they are describing is actually history, okay? The history of what was happening in that part of the world when that sediment was deposited. Because remember, before it can become rock, the sediment has to be deposited. It has to be put down first, right? It has to stop moving, it has to settle, and there remain long enough to be lithified. Now, whatever energy was present, what weather conditions were present, what was the temperature like, what animals lived there, what was the chemistry of the water that it was deposited by, what was atmospheric content like, all of these things can be discovered through an analysis of the sedimentary rocks. And then we can reconstruct an environment from that. My thesis years ago when I was in Louisiana was not, there was some lithologic analysis, okay, of the sediment, but mostly it was focused on the fossils in the sediment to reconstruct a paleoclimate for a local area in Oregon. And using the fossils, I was able to do that, okay? And a little bit of lithological reconstruction. Other people had done a lot of the work on the sediment already, so I mostly just referenced their work to confirm my own, okay? So these things all work together to make this history, to figure out what this history was like, okay? So our environments, I'm going to split them into marine and non-marine environments. Okay, so one went into a hardcore branch of the military, and what? No, that's not what marine means today. Okay, marine means what? Under the ocean specifically. Okay, having to do with the ocean. Non-marine, deposited on land. This includes things like rivers and lakes. Okay, those are deposited on continents, and therefore are non-marine, though they involve water. Okay. So our marine environments include ocean basins, near-shore shelves, deltas, lagoons, things like that, okay? So this marine, non-marine can include everything from soils, lakes, glaciers, deserts, I already said glaciers, rivers, right? All of that, non-marine. Now, we interpret these differently. They mean different things, although there are some shared patterns between them. Okay, for example, energy is energy, right? Whether you have high energy in the ocean or high energy in a river or a lake, it's still going to do some of the same stuff. Higher energy can carry heavier particles, right? And so that pattern remains true. The ways that they're deposited may be different, but there are some shared patterns. Let's start talking about marine sediments. Way out in the ocean basins, do you think we have high energy or low energy?
Low energy.
Low energy, right? Especially the deeper you go underwater, the lower the energy gets. Up near the top, we've got all that wave, those waves from the energy imparted to the water by the wind. But the deeper you go, the less energetic it gets until finally hardly anything moves at all. So do you suppose we'll have larger or smaller sediments? Yeah, the really small stuff, because the high energy that you need to move larger sediments, that's way closer to land, right? Way out in the deep ocean where there's so little energy, only the tiniest little particles make it out there. Your clays and silts, but also a lot of organic stuff, okay? Now, the very fine-grained stuff that settles at the bottom of the ocean, which is sourced from some organic substance, normally from zooplankton and phytoplankton and coccolithophores, radiolarians, foraminiferans, all of these really fun names of microorganisms that live in the ocean. We normally just refer to them all as plankton, right? All of those little things are living and dying in the water column, and as they die, they filter down to the bottom and settle. And we call this ooze. An ooze. You don't like that word, do you? There's always someone in my class who that just makes them okay? So I'm sorry, but I will say it a few more times. There are two types of that word, okay?
You can say it. It's like an interesting word for that.
Silicious ooze and calcareous ooze. Now, why do we call it an ooze? It's not like slime. Normally, when I say ooze, you would think slime, like what you can get in those little buckets at Walmart or something. Right, yeah. It's not really like that. The name ooze actually comes from, I believe, a Latin root word. I'm not entirely sure what it means, and I'm not going to pretend that I do. But I know that what we think of as ooze is not the classic definition of the word ooze, and that's why it's applied here, okay? So silicious ooze is mostly silica-based particles from organisms that use silica to construct their exoskeletons or internal components. Calcareous ooze, what do you suppose that's made out of? Calcite. Okay? So, do you remember the circumstances in which we would have silica-rich shells versus calcite-rich shells? We talked about this in 1403. Bless you.
Please don't looking at the board.
You it's okay. You can look at the board. There's little tips on there.
Assume the water temperature.
The water temperature, exactly. Which is based upon what, primarily?
Energy. Where's located upon the globe?
Geographic location, exactly. Okay, so colder water closer to the poles, warmer water closer to the equator. Warmer water is better for calcite shells. Why? Because calcite dissolves easier in cold water. And if you are an organism that uses calcite for your shell, you're not going to want to hang out in cold water. Your shell starts to dissolve. It gets weaker, right? And so the calcite, the organisms that build their parts, their hard parts out of calcite, stay closer to the equator in the warmer waters. And those that stay closer to the poles use silica. They've adapted to use something different. Okay? So whenever we find a rock that had a significant amount of silicious ooze in it, what is a fair analysis, a fair, I guess, educated guess that I can make based upon knowing that it's got a high amount of silicious ooze in it?
It's based around the poles.
It was somewhere near cold water, probably near the poles, unless other data I find suggests that perhaps there was an ice age at the time. It could have been closer to the equator. But it's fair for me to assume safely, right, that it was probably nearer a pole than it was the equator. And so just like that, I have a general idea of where geographically, at least latitudinally, that rock was formed or that sediment was deposited anyway. Okay? Alrighty, we found one really cool piece of information. Now, what does this ooze turn into? Silicious ooze tends to make beds of chert. You remember what chert is? Microcrystalline quartz. I don't think I have a chunk of it over there. This rock here, this fossilized tree, has been replaced by microcrystalline quartz. Okay, so but instead of making a fossil like that, it would just simply form a bed or a series of chert nodules. If you watch any of my caving videos on my YouTube channel, Heart Rock Geology, you will see that I point out structures poking out of the walls in some of the caves, and they are silicious nodules. Some of them might be sponges, but a bunch of them are probably just nodules that formed from silicious ooze that compacted together. Okay. Now, what does calcareous ooze turn into?
Limestone?
Limestone. Exactly. Okay. Silicious ooze is going to turn into your limestone. It might be fossiliferous. It might not be visibly fossiliferous, but if you looked at it under a microscope, there could be some. Okay. Okay, so that's our ocean basins. When we get closer to shore, we start getting larger particles. Why? Well, energy is increasing. The closer to shore we get, the shallower our water is, and therefore the more energy there is. Okay, it's not dispersed through as much water, and that wave column, that wave energy is closer to the bottom of the ocean at that point, near shore environments. So whenever we get a storm that rolls in, it greatly disturbs that sediment at the bottom, okay? Like if I had a fish tank right here, and I filled it with water, and I had a couple inches of sand, right? And then I took a spoon and I slowly stirred it. It wouldn't really do much with the sand, would it? But what if I really went at it with that spoon? I would eventually disturb the water enough that my sand starts sifting around and moving and getting disturbed, right? That's what a storm does. It disturbs the normal wave base and moves sediment. It'll pick up that sediment and carry it places, okay? So you get more piling up near the shore. That's how you form your barrier islands, things like that. You can also form what are called tempestites. This is a sedimentary structure that we find where lots of heavy storm activity occurs. This will happen in, say, places like Louisiana today, where you have massive hurricanes that move in. What do those hurricanes do? They rip up sediment from the bottom of the near shore and carry it on land and deposit it on, say, sandstones, beach sandstones, okay, beach sands. And so what you'll end up with is a sandstone that is characteristic of a beach sand, but has chunks of clay or silt in it, okay, like you see here. This is a tempestite. Sandstone, sandstone, sandstone. Oh, look at this deposit of clay and silt. Sandstone, sandstone, a little bit more right there. Tempestite. This has been deposited by a heavy storm activity. Bless you. Deltas, another environment that we find in the near shore. Remind me how a delta forms.
When a river connects with the ocean.
Okay, why would a delta form where a river meets the ocean?
Brings sediment, the river.
What's happening to the sediments in the river?
Deposit in the ocean.
It's getting deposited in the ocean, but why? Why doesn't it just keep on going through the ocean?
Because energy's changing.
Why is the energy changing? I'm going to keep walking this back until we figure it out logically.
It loses the energy.
It's losing the energy, but why? You guys are doing great walking backwards down this ladder. We're almost to the last rung.
It went down.
Yeah, I mean, the energy went down, but why?
Or like the sediment went down and down.
Well, the sediment went down because the energy went down, but why did the energy go down? That's the ladder rung we're on right now. Beneath that, why would the energy be lost?
Because there's more water, so the energy like dissipates into the larger.
Bingo! You have a finite amount of water in your river containing a relatively high amount of energy. When it runs into the ocean, all of a sudden, there's way more water, and the energy gets dissipated out into that water. Therefore, it cannot contain the weight of those particles, and the particles fall down. Now, as the particles fall down, it's going to increase the elevation of the bottom of the nearshore ocean, right? And as it approaches the surface, our river has to continually keep pushing its way out to the ocean through the deposits of sediment that it itself is bringing to the ocean. And that is why here, this is the Mississippi River Delta right here, okay? This is why it's pushing so far out into the Gulf of Mexico, okay? It's bringing so much sediment that it's dumping it out here, and you can kind of see where it's actively building out. The darker it gets, the deeper the water is, the lighter it is, the closer to shore, right? You can see where it's building out this entire delta further and further out into the Gulf of Mexico. Okay, that's how a delta forms. Layer upon layer upon layer upon layer, building its way out into the ocean. Now, a lagoon is what we call that strip of water between the mainland and a barrier island. How many of y'all have been to Corpus Christi? Padre Island? Yeah? That is a barrier island, a very long stretch of sand, basically. Here we go. Here's Corpus Christi Bay. Okay. These islands out here, these are all barrier islands built up as storms roll in and push sand up and pile it high, but it never quite makes it to the shore. And so you get these big, long piles of sand in front of the shoreline, and they actually end up protecting it from a lot of the storm activity, which is great and makes for a fantastic vacation getaway. I'm hoping that I can take my family out to Corpus sometime in the next year or two, spend a couple of days out there. They can hang out on the beach, and I can go deep sea fishing. But that's one of the ways that you make a lagoon. You get some very interesting ecosystems that form inside of lagoons. As a matter of fact, some of the most important organisms we are going to learn about, some of the oldest organisms we're going to talk more about, currently reside in lagoons for reasons we'll get into later. Okay? Lagoons tend to be very calm. So what size of grain do you think we'll find in there? Very small, exactly. So When we have a lagoon, we typically have, when we're looking at this geologically, we'll have sand wherever that barrier island was, and then more sand wherever your beach on the other side of the lagoon is. But between these two layers of sand, we will have what are called tidal channel deposits and lagoon sediments, both of which are very fine-grained, clays, silts, some organic remnants, things like that, because this barrier island is absorbing all the energy from the wave activity. Now, when the tide goes out, all the water in this lagoon gets sucked out between these barrier islands and leave either very shallow water or no water at all. We call that a tidal flat. And then when the tide comes back in, whoosh, it gets covered in water again. Fossils that are present in marine sediments. There are so many. Remember, life has been present in the ocean for far, 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 far longer than it was on land. Okay? Matter of fact, there was hardly any land at all when life actually started, way back as far as we believe it did. Okay? Not nearly as much land above the surface of the ocean as we have now. Now, reef systems, some form of reef system, are typically what we find large groups of fossils having lived in. Okay? A reef is a community, and a community is a group of populations within a given area. Okay? So today, when you look at a coral reef, what do you see? You see coral. I already just said coral, but they weren't always coral reefs. You see coral, you see sponges, you see algae, you see bryozoans, you see clams, you see oysters, you see lobsters, you see octopi, you see all these things all living together in a community, right? That sort of behavior has been around for a long time. Now, where do reefs form? Do they form way out in the deep ocean? No. Why?
Too little stuff.
Too little what, though? Food, sure. And also light. Many of the organisms that build up these reef systems are photosynthetic, or some part of their life cycle relies upon being in the photic zone. That photic zone is the depth of water that light can penetrate. It's usually 300 to 600 feet. Okay, 600 feet is typically as deep as the light can go. 300 if it's a little murky water, right? But 300 to 600 feet, that's your photic zone. Most of these organisms that form coral reefs today, I'll talk about the different types of other reefs that formed back then later, but they are photic for the most part, okay? So they need to be in that zone where the light can penetrate. So they need to be near shore, okay? Not necessarily on the beach, but near shore. If you've ever gone to Hawaii or any other island and gone snorkeling, you need to swim out a couple hundred feet before you reach the reef, typically, okay? Now, these reef systems have since become limestone, fossiliferous limestone. I gave you a good example of one that's not far from us, the Guadalupe mountain range. Massive reef system, right? Here's Texas. Guadalupe is out here, right? Out in this area. Massive reef system. But it's not the only one. We've got a very curiously shaped reef system right here. Why do you suppose we will find reefs? We call these atolls, by the way, when they're circular shaped like that. Why do you suppose we have a giant atoll right there? This is what happens when a reef builds up around a very particular shape in the ocean, a shape that has to come up close enough to the surface that these photic organisms can start growing around it. What kind of shape, what kind of structure could that be? A volcano. Exactly. When you have a volcano out in the ocean and it grows and it grows and it grows up to near the surface or even out of the surface of the ocean, you will get this ring of growth around the edge. All these organisms that build up around it. And after the volcano is dead, it is not spouting any lava anymore. It's not growing. As a matter of fact, it's falling apart as weathering and erosion take their toll. Okay? You get the continued growth of these organisms around it until finally you hardly have a volcano at all, but you still have this circular ring of reef. And then finally, volcano is totally gone, but you still have that ring. We call that a lagoon. That is a lagoon, but the structure itself is an atoll. Okay? A-T-O-L-L. So take a look at this atoll that we've got here. What a volcano that must have been. Right? It's a huge atoll. And how long that volcano must have been there for it to be that big. Right? All limestone now. But we know what this is, and what it means was there because we see the same thing happening today. Principle of uniformitarianism in action, eh? Right? Yeah. Okay. A little bit more about fossils. When you have very warm, shallow seas with lots of things living in them, and those things die and they fall to the bottom, yeah, sure, you're going to get a buildup of all that calcareous ooze. But because that turns into such a thick deposit in warm, shallow seas where calcite-rich organisms are common, we tend to call those carbonate platforms. Okay? These end up in tropical places mostly. Here we have a picture of the Bahamas. Okay? So this is a depth chart. Anywhere that is blue to light blue, like out here, that's fairly deep water, 5,000 to 10,000 feet. Anywhere that is white, that's only 500 feet. But look how far from land this stretch of only 500 feet goes. This is a carbonate platform. Very shallow water, relatively shallow water, right? 500 feet is still really deep. I can't go that deep. I don't know about you guys. But it's still pretty dang shallow for how far from the nearest land it is out here, okay? It's a carbonate platform. So many things are living in this water that their depth and buildup on the bottom of the ocean has actually raised the bottom of the ocean that high. Okay? Now, everywhere you see that has these blue dots or these blue dashes, so here's some dots, there's some dashes, dots, and dots over here. Those are what we call oolites or lime sands. Okay, so perhaps you'll recall I have the oolites here. They look like sand grains, right? But this is entirely calcite. Little grains of calcite that formed in the ocean fell to the bottom and then got rolled back and forth by wave action, making them have these smooth spheroidal shapes. But this is definitely calcite, not sand, quartz, or quartz sand, right? And then stromatolites. I told you a little bit about stromatolites before. Stromatolites are the oldest form of communal, I'll say, life that we know about. Okay? There are stromatolite fossils that are, I believe the oldest one is more than 3 billion years old. I have a stromatolite fossil in my collection. It's either in my, I think I might still have it in a box. I don't think I ever unpacked it years ago, but I have a stromatolite from the Silurian, not nearly as old, but it's still a cool fossil. We'll talk about the Silurian later on in the course. But what happens is you get these algae communities that grow in warm, shallow water. Tide goes out, tide comes back in. What does that tide bring in with it? Sediment. A very thin layer of sediment gets deposited on top of this algae. Now this algae is photosynthetic. It needs exposure to light. So what's it going to do? Grow up through that thin layer of sediment to reach the light again. And so it gets thicker and thicker. And whatever, whatever the bottom, whatever the surface of the ground that it was growing on, it's going to gradually kind of exaggerate that shape. Okay? So as it grows taller and taller and taller, it's going to start making mounds wherever there was a small increase in elevation and little little valleys wherever there was a small decrease in elevation, right? And so it gets taller and taller and taller as this process happens over years and years and years and years. And then finally, you get our characteristic stromatolite mushroom sort of shapes. There are still stromatolites alive today, by the way. Not billions of years old, but still very old. Okay? Classic example, if you look up pictures of Shark Cove, Australia. Just an entire bay filled with stromatolites. They really only live in lagoons anymore and tidal flats. Why? We'll talk about why in a later lecture. Let's just say it was good for their health. All right? That's marine sediments. Any questions about marine sediment or marine environments? Yeah.
So going back a little bit, so siliceous ooze turns into silica beds, right?
Yeah, often called, well, silica bed is kind of the name for the entire thing, but you can call it a chert bed because the type of rock that we learned about is chert, or a flint, jasper, those are synonymous for it.
Okay. And then the calcareous ooze.
Calcareous.
Calcareous turns it into limestone over time, right?
Yeah.
Okay.
Yep, calcareous ooze will turn into limestone. Good question. Anything else? I want to make sure no one gets left behind. Okay. I'm curious, what are you doing with your scissors? Are you making a new belt loop?
Yes.
Nice, okay. All I saw were scissors and it was just like
yeah,
doing this.
it's
I was like,
'cause it's too big. It was bothering
you
me.
okay? Okay. All right. Soils. Soil is a very delicate balance of mineral content and organic content, and water and air. That organic content, again, is humus, not humus. Okay? Humus is the term for that organic content. Where does it come from? Where do you suppose the organic content for soil comes from? Whatever was living in it and has died in it, right? It's renewed. It's recycled. So grass or oak leaves or pine cones or anything like that, whatever the organic material that was growing in that soil, eventually is going to die and decompose and be reincorporated into that soil. This is a major component of the different ways that we classify soils, what type and how much organic content is in it. Mineral content, that comes from the weathering and breakdown of rock, right? And then obviously how much water and air is in it, also a huge factor. Here in Odessa, do you think we have more water or more air in our soil? More air, right? But if you were to go to the Amazon, you'd probably have more water in that soil, okay? And that also will dictate what kind of things can live in that soil. How ideal is it for certain types of things to grow? You probably would not have much luck growing in West Texas cactus out in the Amazon. But you also wouldn't have much luck growing mahogany trees out here, right? Okay. Now, this mineral content is going to be dictated by a few things. What is your parent material, aka where did that mineral content come from? Was it a granite? Was it a schist? Was it another type of sedimentary rock before? Was it basalt, right? All these chemically different rocks could provide different chemical inputs for the mineral content in your soil. Also, how long has that material been weathered? How far was it transported before being part of that soil? What was removed from it? What is left in it? If it's been transported very far, you've probably just got a bunch of quartz left, right? Not terribly useful for a lot of things to grow in. Some things utilize it a lot, like corn. Side tangent, I'm not a big fan of corn. How many of you like corn? Okay. Most people, corn.
Corn?
Yeah. Most people just like corn because it tastes good. It's really sweet. And that's true. It contains a lot of natural sugars. However, have you ever noticed how difficult it is to chew the outside of the corn kernel? And have any of you, at risk of being gross here, have any of you realized that it's still there the next day after you get rid of whatever you ate the night before? Right? Yeah, I'll put that politically, very delicately. It's there in the toilet, all right, for those of you that didn't catch on. Why? It's mostly silica. Your body can't process it. And so I'm not a huge fan of corn because you don't really get anything nutritionally out of eating it. So I avoid it whenever I can. Also, I hate it when they get stuck in your teeth, right? But yeah, certain things will, they will gobble up, they will love all the silica content in soil, but other things won't. They would rather there would be more phosphorus or nitrogen in your soil, right? Maybe like something like beans, okay? So a lot of factors go into what your soil is good for. And trying to force a soil to grow something that is not ideally meant in nature for that soil, that can raise problems, okay? That's where you get crops that die because the soil cannot support them. Your soil is separated into horizons. We won't spend too much time on this. But you've got your O horizon, which is, I think, O, organic, right? Think of this as decaying vegetation, right? Or decaying anything. This is where you've got your leaves, your sticks, your dead squirrels, your mushrooms, all that stuff, okay? Breaking down the organic content. Underneath of that is your A horizon, your topsoil, okay? Perfect for growing. It's got your mineral content. It's got that organic that's filtered down into it. It's got air and water, all of that. It's great. Then you've got your E horizon. This is where it starts getting a little nasty. Not particularly good for growing much. A lot of clay-sized particles. Then your B horizon, which is everything that's been left over from the above. Okay? And then you've got your breaking down mineral content, your bedrock underneath of that. Glaciers. Glaciers not only are forces of breaking down rock, but they also transport it. They are both forces of weathering and erosion simultaneously. Okay? So a glacier will carry material all the way down to its terminus, where it is currently melting. And so you can have material that is transported hundreds or even thousands of miles. Maybe you'll remember the story I told you of when I lived in Ohio, and there was that giant chunk of granite sitting out there at that state park. There shouldn't have been any granite there. It was transported thousands of miles from Canada by a glacier. Okay? We call these glacial erratics, and we do, in fact, find these in the geologic record as well. We will have layers of tillite, which is, the sediment that is transported and dropped by a glacier. And then there will all of a sudden be a gigantic chunk of something in there, right? Or we'll have a layer of limestone with a giant chunk of granite in it. And why? Well, because the glacier flowed on top of that limestone, dropped a chunk of granite as it was melting backwards, and then more stuff was deposited on top of that. So there's lots of things. Okay, especially interactions where glaciers flow out into the ocean. You can get some weird interactions between different types of rocks and erratics out there. But because we can see how this operates today, this definitely helps clarify some of the more mysterious things that we couldn't figure out before. Principle of uniformitarianism at work. The landforms that are caused by glaciers can also be present in sediments and structures. Okay, so I could have a glacial valley that gradually gets filled in with layers of sediment and then becomes sedimentary rock, and then I can go hundreds of thousands of years later or millions of years later and see in cross section this valley. Maybe small, very large, but filled with sediment. Okay, what made this valley? Well, let's go and explore. Here's evidence of glacial striations, right? So I can say This is a glacial valley from 25 million years ago that filled in with sediment, and I can make all these interpretations because I can see how they are made and exist today. And knowing how to interpret layers of rock, I can say, okay, well, there's tillite here, and then there's sandstone here. Okay, so there was a glacier here X amount of years ago, and this valley gradually became filled in, and there were various rivers that ran through it, depositing all these layers, and I can build my interpretation upon itself, step by step, by reading the pages of the geologic book that is in front of me. So, this just reminding you of a little bit of terminology here, okay? The valley is the main course that the glacier takes. The cirque is where you have tiny little side valleys that come and meet up with your main valley, right? Cirque, 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 all meeting up into your main glacier here. And a fjord is what we call it when all that ice is melted, and therefore sea level does what? Rises, because all that water went from the glaciers back in the ocean. So your water level rises, and your glacial valleys that were right next to the ocean are now submerged in the ocean. That's what a fjord is. When we see a roche montagne like this, we can get an idea of which direction glaciers came from, right? Because it will scrape this hill or whatever this feature was. It'll make this long, low angle slope in the direction that it came from. So I can tell where the glacier came from simply by looking at that feature. Okay? Some interpretations we can make. Your glacial till, right? That's the name that I prefer, also known as glacial drift. So if you go and you do your own research, you may see either one of those words used to describe the sediment that is dropped by a glacier. By analyzing the composition of that till, you can make a determination for what material that glacier plowed through, right? How long ago did it do it? How broken down is that material, right? Glacial flour, that very, very fine pulverized material. If you've ever held flour in your hand, it is such, they are such small particles, it almost feels like a liquid, right? That's how fine this material has been pulverized by the glacier. It gets deposited in layers at the base of the glacier, wherever it is actively melting, wherever that water is flowing away from the glacier. It's taking this glacial flour with it. And the thicker the layer of glacial flour, the longer the season of melting was. The thinner the layer, the smaller the season of melting was. So if I have thick, thin, thick, thin, thick, thin, I can reasonably assume winter, summer, winter, summer, winter, summer. And I can track by counting how many and how thick these layers are, how long that flour has been deposited in that location, which gives me an approximate idea for how long the base of the glacier was there. So I can make an interpretation like, how long has this glacier been retreating backwards? How long has it been advancing? Has it stayed there for a long period of time? Right? Now, if I have a very thick layer of rock flour, okay, that may indicate to me a very hot year, an extended summer, very hot spring, very hot fall, plus the summer, lots of deposited. If I have very thin, very thin, very thin, very thin, very thin pile on top of each other, that may indicate to me there was a period of global cooling. Okay? Glacial moraines, these are the conveyor belts of sediment making their way down out of the glacier. Okay? So you've got your lateral moraines that occur on the sides of your glacier, right? As the glacier is scraping material off the side of the rock, off the side of the valley, it makes this lateral moraine that travels downhill with the glacier. Where two glaciers meet up, the two lateral moraines converge into a medial moraine, which continues its path down the glacier. Where lateral moraines and medial moraines dump sediment at the bottom of the glacier. The glacier is melting and all the sediment that's been carried downhill with it is getting dumped out. That pile of sediment at the base of the moraine, we call that a terminal moraine. And we can find both lateral, medial, and terminal moraines in the geologic record. Any questions about glaciers or soils or anything? All right, well, let's talk about deserts then. What sort of features, what sort of structures or rock types do you suppose we could find that may cause me to wonder if I'm looking at a desert environment?
Can you repeat that?
What sort of rock types or structures could I find that may cause me to think I'm looking at a desert environment? What? Well, a dune occurs in a desert, right? If I'm looking at a dune, I'm obviously looking in a desert or a beach environment, perhaps. But what would a dune look like in sedimentary rock? Do you remember? A dune is a pile of sand getting pushed in one direction by wind. Kind of looks like a sand wave, but when you have a dune and a dune and a dune and a dune and a dune, and after all this time, different dunes get piled on top of each other, what sort of structure do you think that's going to make in our rock? What do we call it when layers of sediment are deposited on each other at different angles? Cross-bedding. Cross-bedding is very good characteristic structure for a desert environment where dunes are being pushed on top of each other. Excellent. What type of rock would we probably be looking at in a desert environment? Sandstone. So we're looking at cross-bedded sandstone. I might be looking at a desert environment. Okay? Now, why do these deserts form? Well, there are a couple of reasons. Latitude, for one. You get hot air at the equator, where the temperatures are hottest. That causes more evaporation of water. That water rises up into the atmosphere. Hot, humid air rises up into the atmosphere. Once it reaches a certain elevation, it starts to cool off. As it cools off, it starts to rain out that humidity. That's why the tropics are always very rainy. It's raining all the time over there. But as it is raining out its water, it's getting shoved either to the north or south by the new rising air beneath it. This is convection. Remember that? And so this air is cooling off more and more and raining out more and more of its water the further north and south it goes, until finally, by the time it reaches the ground again, somewhere around, it's like between 30 to 23 and a half or something like that. I don't remember the exact, but there's a strip right here, okay, around the tropics of Cancer and Capricorn, where cool, dry air is now interacting with the surface. That cool, dry air cools and dries the conditions at the surface level. And you end up with mid-latitude deserts, right about where we live. It's a huge part of the reason why conditions here are so dry. Okay, we live approximately around where, here, right? We live right there. Look at that. Couple other reasons. We could be looking at a landmass so large that the interior is far enough from a source of water, it doesn't receive as much rain. We know this happens. As a matter of fact, Well, Pangea was still around. You remember Pangea? We saw that video in our last lecture, right? Pangea was a mass of land so large that a humongous amount of its interior was desert. So much of it was far from the ocean that hardly any rain went into the inside. So there was a huge desert. That's not the first time that's happened. Anytime there's a massive supercontinent, there's usually huge deserts associated with it. Also, a rain shadow desert could be a candidate situation. Rain shadow deserts happen whenever a mountain range is blocking the source of water from a certain geographic region. So here is the Andes mountain range. Here's the Amazon rainforest. And here, a desert, the Atacama Desert. Right? Why is that there? Because the wind is blowing this direction. Nice, humid wind coming off the Atlantic. It runs into the Andes. As it runs into the Andes, it climbs up into the atmosphere. As it does, it cools off, rains out all that stuff into the Amazon, so only cool, dry air makes it to the other side. There's no wind going that way. So none of the humidity from evaporation over here is going that direction. Only wind is going that way. And therefore, we have a desert, even though there's an ocean right there. Okay? Rain shadow desert. All of these are products of tectonics. So if I'm looking at a layer of rock and I can confirm this looks just like desert material, it's safe to assume one of these situations was true of this geographic area during that time. Right? I can make interpretations about the environment based upon what I know. Other evidence I may be looking at a desert, we've got deflation of sediment, right? So I could have a whole dune system off this way and a whole bunch of desert pavement deposit over here, right? Just a whole bunch of cobbles and gravels next to this cross-bedded sandstone, indicating, yeah, more evidence of a desert environment. A ventifact. Remember that ventifact, those sand-blasted, wind-polished rocks, as the wind is constantly being blown around by the wind. It's sandblasting the rocks in the area. As it sandblasts all of those rocks, it smooths them out. We can find those in sedimentary rocks. Chunks of super smooth material. As a matter of fact, remind me before I end the recording today. I'm just going to do it right now. I'm going to grab something from my office. I'll be right back. It's too cool not to show you.
Now the camera's looking way out.
Oh,
Say hi.
it's on you on the ground.
It's always on me. Do the hand signals. That one works, I guess.
All right. Put my microphone back on real quick.
Your camera.
That's fine. Needed to come over here and grab my microphone anyway. All right. Hey. All right. What do I have here? I brought some marbles. Marbles. But these aren't your normal marbles. These have taken on this spherical shape only because of wind. Pass those around here and start these ones over here. The wind in a desert environment takes chunks of sandstone and blows it around and blows it around and moves it and shifts it and tumbles it until the corners wear away. And as it becomes rounder and rounder and rounder, it can move easier and roll more. And it gets rolled this way and that way until finally you end up with a sphere. This is an example of the sort of feature that you can expect to find in a desert environment. You just put them down over there and I'll get them in a minute. Pretty cool, huh? Some people told me that at one point, like, there are places around the U.S. where they find those, and they call them, I think that he called them Navajo marbles, because they did use them for games. And some people did, in fact, think for a while that that's how they were made. Like Native Americans would carve them into that shape, but we know better now. Those are formed by the wind. I've actually out in several deserts, 2 different locations, one in Montana and one in, where was the other one? Utah. Actually pulled those out of the rock that they had been encased in, because sometimes they'll form and then they'll get incorporated into new sediment, right? Okay. You okay? No? All right. And then a yardang, right? This is what happens when you get a large geologic feature that gradually gets worn away faster at the base than it does on the top. Why? Because the sand, the heavier particles, are getting blown along the base. So that sandblasting effect, the same one that made those marble structures, occurs at the base of your structure more than it does the top, and you get this mushroom shape. That's a yardang. We already talked about dunes a little bit, but just to reiterate, I'm not going to go over the different types of dunes, but a dune is what happens when sand gets blown into a pile, thanks to aerodynamics, as wind is blowing in a certain direction. Okay? And so you get these piles of sand that are migrating across certain distances. Yes, they move. There are several communities in the western United States that have this ongoing struggle where they are constantly having to move sand out of their town, because dunes don't care that there's a town there. They are going in the direction the wind is pushing them. And so I've driven through towns where there are dunes literally crossing the street. I'm not even joking. It might take a few weeks, but the dune will cross the street on its way through town. They just have to go around it or plow through the dune. And then loess is the name that we have for the sand, or the silt and clay-sized particles that are formed in deserts, and it gets blown around. It goes all the way across the Atlantic Ocean sometimes, right? Here's some African loess getting blown across the Atlantic out here off of Central America. Okay. So this is also very cool, by the way, because we can find chemical evidence of deserts preserved in ocean rock, right? The layers of shale way out here in the deep ocean do have some African dust in them, and we can find it by analyzing that rock. So by doing the same thing from rock a lot longer ago, a lot further back in time, we can figure out if similar situations occurred. Come on, computer, catch up here. Don't lock up on me.
And like the sand has to do what, like, there's no clouds in there.
Oh, here we go. Okay, what was that?
That there's no clouds in that area.
No, there were clouds. It just depends on the time of year how many clouds. The clouds don't really have any influence on whether or not the dust makes it across the ocean. The strength of the wind at the time does. Yeah.
Where does the dust land?
Oh, all along that route. So it'll fall down into the ocean as, across the Atlantic, which is why we will find layers of African dust in the shale at the bottom of the Atlantic. But also some of it does make it across to Yucatan and southern Mexico.
Does it make you sick?
To the Caribbean.
Oh, I've heard of this before.
Yes, it does.
I have heard this before. People claim that the dust from Africa blowing across to Central America is making people sick. How good does it feel to breathe in any dust? Not good at all. So yeah, I'm sure breathing in a lot of African dust, whether you're in Africa or in Yucatan, doesn't feel great. It's not because it's coming from Africa, if that's what everyone's
No, no.
wondering.
Color change.
Dude, I'm saying the dust makes you sick.
You said the African does make sense.
Okay, I'm still right.
Now, not much of it makes it over there. Like, there's a lot more dust in Africa than makes it to Yucatan. But if you're not used to breathing that in, it could potentially create negative health effects. Yeah. I know that there are some people that are investigating that at the moment.
We had literally to put like masks because the dust you could see it in the air, and then you put masks because you can get sick.
Yep. I'm curious, whenever we have a dust storm here in Odessa, does anyone put a mask on? Yeah, I don't really. Although they are really impressive here. For anyone who's watching this who is not from Odessa, we get some impressive dust storms here sometimes. Like I have a few memories. For some reason, we always get them when I'm coming out of Walmart. I'm not sure why, but I'll be walking out of Walmart and there's just a wall of orange right there. Blue skies, nothing off that way, wall of orange moving into town. And I'm like, oh, here we go again. Okay, get back to my car, and then all of a sudden visibility is down to 20 feet, you know? It's quite impressive. All right, back on track here. So when I showed you this model before, it was simply to show you how the river moves around and how it'll cut off and how it'll get back on track and all of that. I was only commenting on the course of the river and how it takes. Now let's look at the way that it is removing material and depositing material. So right here, where you see this cross section of this river, I want you to watch that. It's going to be fascinating up here, sure, but I want you to watch this cross section. What you're going to see is as the river is carving material out of this surface, it's also going to be depositing sandstone along the course that it goes. So it could be, who knows what this material is, right? But it is going to be depositing layers primarily of sandstone. We typically think of this as mostly sandstone at an angle depending on where the river's course is going at that time. Okay, so watch that cross section. See how it's depositing at this angle? And now a new branch of the river came through and removed it. And now it's depositing right there. This river always depositing, always removing. Depositing. And then this is going to come through and carve some. Now it's depositing again, chewing away, depositing, gradually creating this river valley.
Does it eventually just become straight? Or it just keeps on going like that?
No, as a matter of fact, the closer this gets to sea level, the wider your river is going to meander. Why is a river moving at all? Yeah, it's flowing, but why? Huh? Gravity's making it move. Where is gravity trying to take it? Sea level. When water is at sea level, it does not move. So all rivers are always trying to get down to sea level. That is why they flow to the ocean. The steeper your angle is, the straighter your river moves, because that's the way gravity forces it. It has more energy if it's on a steeper slope. On a gentler slope, gravity's still making it move, but it's not as straight a course. It meanders like this. And so as we carve our river valley deeper, and the more of the river gets closer to sea level, it's probably actually going to meander even more, not go straighter. Yes?
So if you look at the Grand Canyon and like at the very, very bottom of it, you can see that like sandstone sediment, right, going in a direction.
So the Colorado River is depositing sediment, but it's chewing through the gneiss at the bottom, okay? The rock type gneiss, okay? The Grand Canyon is very interesting geologically because there is a couple billion years, I think it is, of missing history represented there. I don't remember the exact number, but there is a lot of history missing in what we call the Great Unconformity. So you'll go from rock that's a couple 100 million years old to like 1.4 billion, or I don't remember the exact numbers. I should, but I don't. And there's a lot of missing time. And so the Colorado River right now is chewing through schist and gneiss that is extremely old, metamorphic rock. So it's depositing some materials, but mostly it's carrying it downstream. Okay, good question. Lydia, did you have a question earlier? I thought I saw your hand up. No? Okay. All right.
And what about the underground rivers? You know,
Oh yeah, what about those underground rivers?
where they go?
They go to your imagination.
Oh yeah.
Yes.
Oh.
No. While there are caves that do have moving water in them, underground rivers
Yeah.
are not real.
That you can find with the things.
Right, that you can find with the copper rods,
the
right?
magnetic
Yeah, dowsing rods. Yeah,
and the
no.
magnetic field,
Yeah, it is. Yeah.
My
Huh?
future career.
That's your future career. You're going to be a dowser. Good.
Uh-huh.
Good. What were you saying, Aaron?
We love our underground rivers, you know.
We love our underground rivers.
Yeah.
Yeah.
I think it's better than like I've been a geologist, you know,
Uh-huh.
searching water, underground rivers.
Hey man, if you can make a living off convincing people that you can use 2 copper rods to find them water,
How are they called? I'm not searching them up.
dowsing rods.
With
Like,
D,
just feel it.
Yeah, with a D.
dows, with
Okay.
dowser.
Okay, this is what your more straight high energy rivers look like. They are called braided rivers, okay? So they do kind of have multiple channels that they take, but the overall course of your river is much straighter. This is what happens when you have high energy from high angle, okay? These carry lots of large particles with them, gravels and cobbles and all of that. So when we find deposits of large grain sediment like conglomerate, we will often tie that to a more braided river situation versus a meandering river situation. All right, lakes. Lake deposits, or lacustrine deposits as they're often referred to, can come in a couple of different varieties, but for the most part, they tend to have a kind of a ring of larger sediment, like gravels and sands, and then closer to the middle, you get the smaller particles get. Why? Because lakes get deeper, closer to the middle. Deeper water, lower energy, smaller particles. Wind-blown dust falls into your lake, sifts down to the bottom in the middle, right? And so those tiny little layers of sediment at the middle of your lake can actually be very, very useful. Because along with that sediment, you're getting things like pollen. Okay? Pollen is something that more and more people are using to analyze paleoenvironments. Palynology, it's called. If you can tell using microscopes the difference between different kinds of pollen, and you know the evolutionary history that led one to the other, man, those people are making good right now. Not only for the paleoenvironmental business, but also the oil industry. They're figuring out more and more how you can use pollen in situations where there were no foraminiferans or other planktonic organisms.
Like pollen from the plants.
Pollen from plants. It goes everywhere, man. It gets blown into the ocean. It gets blown into lakes. It gets incorporated into everything. There is a long history of pollen on our planet. And learning how to analyze that pollen in these thin little layers of shale in the ocean or in the lakes is proving more and more useful in the oil industry and in other fields as well. Okay? But look how tiny, look how incredibly thin these layers of sediment from this lake deposit are. That's a penny for scale. Look how thin those are, right? Each one representing a different depositional sequence. A thicker layer for, say, a warmer season, where there is more water moving into the lake carrying sediment with it. A thinner layer may represent a drought where there's no water, or a winter where most of the water is frozen and nothing's flowing in. Okay, so we can make interpretations using that. Every now and then we'll find one of these, an erratic, like that. This is clearly a gneiss, but it is trapped in layers of shale. Look at these thin little layers, right? This rock fell down into this lake, possibly from a cliffside, and was incorporated into the layers of shale. It kind of pushed down on the layers of mud beneath it. You can see where it squished the mud down, right? But then more deposits were on top of it, and the entire thing got compressed into shale with a chunk of gneiss in the middle of it.
Question.
Yeah.
So rock skipping, right? So it's like particularly at lakes. Do you think this is happening with the rocks that were throwing directly in the middle of the lake, or is it too much or is it too small to have like any effects?
If you went out to a nice calm lake and you did the perfect skip, you got 12 skips. It went 200 feet out into the lake. Your rock would settle down to the bottom, be incorporated into the mud, and then in a couple million years, a geologist could dig that particular layer up and find your rock and be like, huh, why is this abnormally flat, perfect for skipping rock out here in the middle of this lake deposit? Right? Theoretically true. Now, remember that principle of uniformitarianism. Any physical, chemical, or biological process that occurs today also occurred in the geologic past, right? And will occur in the geologic future. So we can look at the way things are happening now to interpret the way things happened then. And based upon what happened then, we can make interpretation for the way things will occur in our future. Okay? A dune structure, which is built on another dune and built on another dune, when turned into a rock, will look like that. Dune here, dune there, dune here, dune there, built on top of each other, making this beautiful cross-bedded structure here. Now, I'm going to add on to the principle of uniformitarianism again. Are you ready? Say it with me now. Physical, chemical, and biological processes that occur now also occurred in the geologic past. And will occur in the geologic future. And occur everywhere else. What do I mean by everywhere else?
Where the situation is going.
I'm going to show you a picture and I want you to tell me what you see. What structure do you see here? Okay, you say a braided river.
Crater. Like holes.
Okay, there are some holes that might be craters. What does this overall structure look like, though? That structure.
River.
River. And what's at the end of the river? Here we have some river channels, but what's at the end of the river? A delta. This is a river delta, characteristic of everything we've seen before. River channels going off this way, delta here, delta here, delta here, just like the Mississippi River. This is on Mars. This is a picture from Mars. Yes, Mars had rivers. Mars had running water. And by the way, for there to be a delta here, there would have to be a larger body of water for that river to run into. Mars may have had oceans. Doesn't anymore, but it did. The same processes that we see happening on Earth happen on Mars. and will happen on every other similarly placed rocky body in the universe, as far as we know. There's absolutely no reason to think that the same physical, chemical, and potentially biological processes that happen here could not also occur anywhere else in the universe. How awesome is that? Fires the imagination, doesn't it? By studying our planet, you are literally learning more about your universe. Okay? And yeah, that is a crater right there. Usually a dead giveaway that we're not looking at a picture of Earth, right?
So like Mars could have like underwater rivers,
Underground rivers.
underground.
No comment. Are you gonna make a business of dowsing for water on Mars now? It'll take a long time before you make money on that. All right. Any questions before we end?
Do you think there's much water down there? Like,
Do I think there is much water down there?
let's say if you were to try it now, or like try to just find water, but you just
Mars is too cold for there to be liquid water. Even the hottest day on Mars is not warm enough for there to be liquid water. So that's why it's all frozen. We used to think that there were only ice caps at the poles. We know there are. We can see them. There are large enough ice caps we can see them from Earth, right? Using a telescope. But now that we have rovers on Mars, we also know that there is ice under the soil. There is a lot of water on Mars left. It's just under dirt.
So we can do this down some distance, is what I'm hearing.
Yeah, but that's easy. It's like, oh yeah, there's water here. There's probably water all over the place, which is exactly how dowsers conned people
No, we search
before.
it out. It says it works, right? We search it out. It says it works.
I'm sure you definitely found a source that says it works. You plead the
And,
fifth. Oh, what was I going to say about Mars? Yeah, it is very possible to have people live on Mars, but they would have to live underground. The temperatures on the surface are too hot, or excuse me, are too cold. You would need to build habitats underground, very well insulated. However, you could harvest water from surface deposits, which would be great, right?
And how do like the animals from deep the ocean get the oxygen?
How do animals from deep in the ocean get oxygen? Gills process water and remove free oxygen from it. Gills, like fish gills,
Or,
like on their necks.
but like how the sun doesn't reach.
The sun?
This,
Yeah, so photosynthetic organisms need to be near the sun, but not all organisms are photosynthetic, right? You and I aren't photosynthetic. We draw our energy from consuming other organisms that have energy, right? If you eat a salad or you eat a steak, you are utilizing the energy that it was stored in another organism. In the case of a salad, a photosynthetic organism. In the case of a steak, another organism that ate a photosynthetic organism. There are producers and there are consumers. Producers tend to be photosynthetic. Consumers tend to be like us, where we consume the producers.
yeah, but like who produces in the deep ocean? Where, what?
That's a very good question. If there are no photosynthetic organisms at the bottom of the ocean, where is the base of the food chain is your question. Excellent question. Chemosynthesis. This is something that we will discuss later on. We have already mentioned it, but we will talk about it more in depth later. In depth, pardon the pun. That was worth a head shake. Chemosynthesis versus photosynthesis. Chemosynthesis is when you take chemically active bonds, okay? So something, say a bacteria that can strip the oxygen out of a sulfur dioxide, okay? So they'll take that, they'll strip off what they need and release what they don't, and that's how they generate their energy. This happens a lot at the bottom of the ocean around black smokers, which you remember are kind of the vents that are spitting all of that metal out near divergent plate boundaries. There are so many chemosynthetic organisms down there, and other things, fish and crustaceans, they go and they eat the chemosynthetic organisms. And that's where the food chain begins, deep under the water. Where it's photosynthetic up here near the surface, the base of the food chain is chemosynthetic deep under the ocean. Fantastic question. Anything else before I assign our next lab? No? Okay, well, let's talk about lab 2. All right. Now, I'm just going to skip all the way through this. Remember that stratigraphy is the sequence of layers of rock and interpreting that sequence, okay? So for this lab, let me just skip all the way to the exercise here. Using all these tools and everything you've learned, okay, you are going to be getting something like this. This is called a stratigraphic column. With a stratigraphic column, you are basically, this is what we would do if I was standing at an outcrop right here, and I see I've got 10 layers of different types of rock here. I would make a stratigraphic column. I'd make rows that represent each layer of rock, and I'd separate those rows into different designations. I would describe the grain size of each layer of rock for each row. I would describe the type of rock that it is, lithology. And then I would provide a detailed description in words for each layer. This is a basic stratigraphic column. Utilizing this method, I can hand that to any geologist, and that geologist can look at what I've got and have the fundamentals of that entire sequence of rocks. Okay? Bless you. So this is what you're going to do. For grain size, you are going to use one line. That one line is going to continuously move up and zigzag back and forth based on what the grain size is for that distinct layer of rock. The grain sizes are separated into gravel over here, which is 64 to 4 millimeters, and then sand in this middle column, very coarse, coarse, medium, fine, very fine, and then silt, and then clay. So this one line is going to zigzag back and forth around those sizes depending on what the grain size is for that layer. You following me? Now, what about lithology? Look at these symbols. Each one of these symbols represents a different type of rock and structures in your rock. Structures that represent cross-bedding, that represent fossils. Okay, and I have given you the key. Okay, using this key, you are going to provide the lithological symbols for each layer of rock. This is what it will look like. This is a blank copy. The one that I give you on the lab actually is partially filled in already. There is a section on the lab where you only have to do grain size and description. I have given you this. There is a place on the lab where I have given you lithology, and you have to give me grain size and description, so on and so forth. Okay, I always give you at least one thing for the entire sequence. You have to provide the other two based on the one piece of information that I gave you. Any questions about this? Yes?
So it says on here that we have to print it out and then do it by hand.
Printing it out would be by far the easiest way to do this because you need to put the symbols in there for lithology. And it would be a lot easier to do that with a pencil or a pen, or even colored pencils if you wanted to, than it would to try and meticulously make each symbol on your laptop. And then make sure you paste it in the right place. Easier to do by hand by far. If you need something printed out, the LRC has that. Maybe you have printers at home. If any of you want to work on this here in class today, I can probably print out a few copies. Any other questions? There was one over here, I think. No? Claudia, Zara, how you feeling? You have any questions about the lab? Okay. In that case, I'm going to end the recording here and we can get started.